Hi students, this is chemistry second chapter, that is electrochemistry. The definition is, in any process, if electrical energy is converted into chemical energy or chemical energy is converted into electrical energy, that process comes in electrical science, nothing but electrical chemistry. So the definition is, the branch of science deals with conversion of electrical energy into chemical energy and vice versa is called electrochemistry. So here some definitions are there based on conductance. Based on conductance, the substances are classified into three types. They are conductors, insulators, and third one is semiconductors. First one, conductors. Conductors means the substance which allows, that means which exhibit electricity through it, is called conductors. For example, metals, alloys. Alloys means mixed metals. For example, steel, bronze, brass. These are alloys. All these contains two or more metals. So these are conductors because they can exhibit conductance when electricity is passed through them. For example, take iron rod. If we pass electricity through iron rod, if we touch that iron rod, we get electrical shock. That means that iron rod exhibits conductance. So that is why that substance is called conductor. Next definition is insulator. Insulator means the substance which does not exhibit electricity through it. That means which does not allow electricity through it is called insulator. For example, wood, rubber, glass, all these are insulators because when we pass electricity through them, they will not exhibit any electricity. So that is why these substances are called insulators. And third one, semiconductors. Semiconductors means, semi means half. That means these substances exhibit conductance partially, not completely. That is the meaning of semiconductor. So the definition is, the substance which allow electricity partially through it is called semiconductors. Examples, silicon and germanium. These are the only examples for semiconductors. Next one, some more types. These are conductors are classified into two types. Conductors are classified into two types. They are electronic conductors or metallic conductor. That is also called metallic conductor. That means the definition is, if a substance allows electricity by the passage of free electrons, is called electronic conductor. For example, metals. All metals comes under this category because if you take iron rod, that iron rod exhibit electricity when we pass electricity through it. That is due to presence of free electrons. That means if any substance having free electrons, then that substance exhibit electricity when electricity is passed through it. So all metals comes under this category. So this is also called metallic conductor because metals exhibit this conductance. Next, second category, that is so there are some more points regarding this one. That is, as the temperature increases in metallic conductors, as temperature increases, the kinetic energy of metal ions increases. Then those metal ions oppose passage of free electrons. Automatically, if they reduce passages of free electrons, its conductivity decreases. So this is very important point. In case of metallic conductors or electronic conductors, if temperature increases, its kinetic energy also increases. Which kinetic energy? Metal ions kinetic energy. Then those metal ions oppose passage of free electrons because those metal ions attracts electrons. Automatically, the passage of free electrons decreases, then conductivity decreases. This is very important point. Next, one more point. During passage of electricity, there is no change in the matter. That means, in the same example, take iron rod. If you pass electricity through that iron rod, then that iron rod exhibit conductance. We know that very well. After that, after electricity removes, then there is no change in matter of or composition of iron rod. That means its weight remains the same before and after electricity. So that is the meaning of this point. So during passage of electricity, there is no change in the matter of electronic conductors or metallic conductors. That is the first category. Second one is electrolytic conductor or ionic conductor. In the previous case, electronic conductors are metallic conductors. This is electrolytic conductor. Here the definition is, if the substance which allow electricity by the passage of free ions is called electrolytic conductor. That means if a substance having free ions, when electricity is passed through that substance, automatically that substance exhibit electricity. That is why those substances are called electrolytic conductors. That is also called ionic conductor. Why it is called ionic conductor? Because that conductivity is exhibited by ions. Next, here the examples are hydrogen chloride, HCl, NaOH, NaCl. All these are contains ions, so they exhibit conductivity. Here there are some more points as in previous case. That is, as temperature increases, conductivity also increases due to increase in number of ions. That means in this case, if temperature increases, automatically number of ions increases. If number of ions increases, automatically its movement increases, conductivity also increases. In previous case, temperature increases, their metal ions increases, passage of free electrons decreases, automatically its conductivity decreases. So don't get confused. In case of electrolytic conductor, that means this, in this one, conductivity increases due to number of ions increases as temperature increases. In case of previous case, conductivity decreases when temperature increases. Next, one more point. During passage of electricity, then composition of matter changes. That means, suppose for example, if you take 1 gram NaCl, 1 gram aqueous NaCl, when we pass electricity, it can exhibit electricity through that solution. After that, that means after removing electricity from that solution, the weight of 1 gram NaCl changes. That means definitely its amount reduces. That is due to passage of number of ions. So the point is, during passage of electricity, in this case its composition changes, but in previous case its composition never change. So this is about electrolytic conductors. Next one, electrolyte. Electrolyte means the dissociation of substance takes place by the passage of electricity, and conduct electricity is called electrolyte. For example, take aqueous NaCl. If you pass electricity through aqueous NaCl, then that aqueous NaCl exhibit conductivity, so that aqueous NaCl considered as electrolyte. So electrolyte definition is, if you take any substance, when electricity is passed through that substance, if that substance undergo dissociation by exhibiting conductivity or electricity, then that substance is considered as electrolyte. For example, in case of iron rod, the iron rod exhibits conductivity when electricity is passed through it, but in that case that iron rod cannot be dissociated. That iron rod cannot dissociate, so that iron rod is not considered as electrolyte. So when electricity is passed through particular substance, if that particular substance undergo dissociation by exhibiting electricity, then that substance is called electrolyte. So that is the meaning of electrolyte. Next one, this electrolyte is 3 types. That is strong electrolyte, weak electrolyte, and one more is non-electrolyte. There are 3 types. First one, strong electrolyte. Strong electrolyte means the complete dissociation of substance takes place but the passage of electricity is called strong electrolyte. Complete dissociation. That means, suppose if you take 100 NaCl molecules, when we pass electricity through 100 NaCl molecules at a time, if 100 NaCl molecules undergoes dissociation, then that NaCl is considered as strong electrolyte. Suppose out of 100, 90 molecules undergo dissociation, the rest of 10 molecules does not undergo dissociation, then that is not a strong electrolyte. So that is the meaning of this one. So when a substance undergoes complete dissociation by passing electricity, then the substance is called strong electrolyte. For example, all strong acids, all strong bases, and salts. Next one, weak electrolyte. I told you just now, what is the weak electrolyte? If it is not dissociated completely, the substance which does not dissociate completely by the passage of electricity is called weak electrolyte. Example, all weak acids, weak bases. I told you already what are strong acids, strong bases, weak acids, weak base in class 11 ionic equilibrium. Then if you see that one, you can find it. What are strong acids, strong bases, weak acids, weak bases. Next one, non-electrolyte. Non means does not. Non means does not here. So the substance does not conduct electricity in aqueous state or in molten state is called non-electrolyte. For example, sugar solution, glucose solution, ethanol solution. That means when we pass electricity through these solutions, these solutions do not exhibit conductivity. That is why this is called non-electrolyte. So this is all about electrolyte. Next one, resistance. I think it comes in physics. That is resistance. Here the definition is the opposing force acting against flow of current is called resistance. That means opposing force. Opposing force is called, simply opposing force is called resistance. According to Ohm's law, R is proportional to L by A, where R is resistance. That means when resistance is directly proportional to length of the electrode. A, capital A means area of cross section of electrode. When we remove this proportionality, then we get one constant here. That constant, this is rho. This is rho. That constant is called resistivity. So rho is called resistivity. Here we should know some more points regarding this one, that is dimensions, units. Here rho unit is for resistance, or unit is ohm. This is the symbol for ohm. Next one, conductance. So the reciprocal of resistance is conductance. We know that already. Or we can say one more definition, that is how much electricity is exhibited by the substance. How much electricity, or the substance carrying how much electricity, that is also called conductivity or conductance. So one more definition is the reciprocal of resistance is called conductance. Here this conductance is represented by capital G or C, capital C. So the formula is G is equal to simply 1 by R. In case of resistance, unit C is ohm. In case of this one, units are, this is the reciprocal, that means ohm inverse, that is also called mho, MHO. Here one more word is there for this, that is Simon. This is represented by S. So Simon or mho or ohm means all are same. Next definition is resistivity, not resistance. This is resistivity. This is represented by rho. This is also called specific resistance. That is also called specific resistance. Here the definition is, see carefully, it is defined as resistance. That means it is also called resistance when the length between two electrodes and area of cross section are unity. That means we know already R is equal to rho into L by A. This is resistance, resistivity. This is resistance. Suppose when these two, that means this is length of electrode, this is area of cross section. When these two become one, automatically this is resistivity is equal to resistance. That is the definition. It is defined as resistance when or if the length between two electrodes and area of cross section are become 1. So the formula is rho equal to r in rho is equal to r by L by A, where r equal to the units for r is ohm, by L in case of CGS centimeters, or in case of SI system meters. You can take anything, where A is area of cross section, that means centimeter square. Finally you get ohm into centimeters. These are the dimensions. These are very important for 1 mark questions. What are the dimensions for resistivity or resistance? They may ask such type of questions. Next, in case of SI system, ohm into meters. Next definition is conductivity. This is represented by capital K. This is also called specific conductance. Conductivity or specific conductance, same as resistivity or specific resistance. So definition is the reciprocal of resistivity is called conductivity. The reciprocal of resistivity. In case of conductance, we have told the reciprocal of resistance is called conductance. Like that, here also the reciprocal of resistivity is called conductivity. One more definition for this is the number of ions exhibit conductance per unit volume. The number of ions exhibit conductance per unit volume. That means in unit volume, how much conductance exhibited by number of ions. How much conductance exhibited by number of ions. That is called conductivity. Units. Before discussing units, we just know that formula. K is equal to C into L by A. We derive the formula like this. This is the formula for resistivity. Formula is rho is equal to R by L by A. Here we are discussing the formula for conductivity. Conductivity formula is reciprocal of resistivity. That means 1 by rho. That means 1 by R by L by A. That is equal to L by A by R. 1 by R is nothing. 1 by R means reciprocal of resistance. That means 1 by R means reciprocal of resistance means conductance. That is G. G into L by A. R you can write here C. You can write anything. So 1 by rho means reciprocal of resistivity means conductivity. That means K. So finally we got the formula like this. So this is the formula. K equal to C into L by A. Here C is conductance. Conductance dimension C is ohm inverse. If you substitute here centimeter, then here also you should same dimensions, that is centimeter square. Suppose if you take meter, here meter square. So finally we get the dimensions like this. Next one, molar conductance. These are also very important definitions. Molar conductance. Molar conductance is represented by mu over lambda m, lambda small m. So the definition is the conductance of 1 molar solution. 1 molar solution means the solution of 1 molarity. That means its molarity is 1. That is called 1 molar solution. If that solution exhibit conductance, that is called molar conductance. So the definition is the conductance of 1 molar solution is called molar conductance. Here the formula is lambda m equal to K into 1000 by m, where lambda m is equal to molar conductance, m is equal to molarity, K is equal to specific conductance. So here the dimension is K equal to 1000 into 1000, lambda m equal to K into 1000 by m. We discussed just now regarding dimensions of specific conductance, that is ohm inverse into centimeter inverse by molarity dimensions. We know that already, mole into liter inverse. So if this denominator mole becomes numerator, it becomes mole inverse. You know that if later becomes numerator, then it becomes liter. 1 liter equal to 1000 milliliters or 1000 centimeter cube. That means centimeter cube. This centimeter cube, centimeter inverse becomes centimeter square. So finally these are the dimensions of molar conductance, that is ohm inverse, centimeter square, mole inverse. So the units are here: ohm inverse, centimeter square, mole inverse. If you take SI dimensions, that is ohm inverse meter square, mole inverse. ORR, I told you already, ohm inverse means Siemens. Siemens centimeter square, mole inverse. Similarly, in case of SI dimensions, Siemens meter square, mole inverse. So these are the dimensions regarding molar conductance. Next one, equivalent conductance. Equivalent conductance means the conductance of one normal solution. Normal solution means molar solution means the solution of one molarity. Normal solution means the solution of one normality. Actually, this is the removed. This part is removed from our syllabus 2 years back. Actually, that is one of the concentration. Molarity, molality, normality, these are concentration method, but this part is removed from our syllabus 2 years back, so that we didn't discuss anything regarding normality. So now you just remember, one normal means the solution of one normality is called normal solution. So if the solution exhibits conductance, that is called equivalent conductance. So that is represented by lambda eq. So the definition is the conductance of one normal solution is called equivalent conductance. Here the formula is lambda eq equal to k into 1000 by n, same as molar conductance. In case of molar conductance, m is there. In case of equivalent conductance, n is there. Here also dimensions are ohm inverse, centimeter square. These are the dimensions. You can write the dimensions if you understand the dimensions in previous case. That is about equivalent conductance. Here the relation between molar conductance and equivalent conductance. First we take the formula for equivalent conductance. Lambda eq equal to k into 1000 by n. N is normality. Here one formula is there between normality and molarity. Normality equal to molarity into x. So by using that point, this equation becomes like this. So lambda equal to q equal to k into 1000 by m into x. This part, that means k into 1000 by m is lambda m by x, where x is total charge on anion or cation. So this is the relation between equivalent conductance and molar conductance. This is very important relation for competitive level. In case of competitive level, there are so many bits regarding this one. So you just remember this expression lambda eq equal to lambda m by x. Don't get confused. Not lambda m equal to lambda eq by x. Lambda eq is equal to, that means equivalent conductance is equal to molar conductance by x. Next one, ionic conductance. Ionic conductance means the conductance exhibited by free ions, not ions. Ions is different, free ions is different. That means if ions moving, that means ions are in motion, those ions are called free ions. If ions are not in motion, those are not called free ions. So the conductance exhibited by free ions is called ionic conductance. Here some points are there regarding this one. Ionic conductance is directly proportional to charge. That means if charge increases, ionic conductance also increases. And next one, if this ionic conductance is also inversely proportional to size. That means if size increases, ionic conductance decreases. And last one, if a number of ions increases, then also ionic conductance increases. So these are the three factors regarding ionic conductance. For example, I take 3 ions, Na plus, Mg plus 2, Al plus 3. All are ions. Let us assume all are free ions. Among these 3 ions, which will exhibit more ionic conductance? Which one? This one. Because in this case plus 3, that means charge increases. If charge increases, positive charge increases, its size decreases. That means in third case charge increases, size decreases. So that this Al plus 3 exhibits more conductance, more ionic conductance. After this exhibit more conductance because here charge is plus 2. That means compared to here charge is more. And if in case of cations, if charge increases, size decreases. So that compared to this one, this will exhibit more ionic conductance. So the order is like this. Next, one more thing, one more example. NaCl, MgCl2, AlCl3. I took 3 salts, NaCl, sodium chloride, magnesium chloride, aluminum chloride. Among these 3 substances are among these 3 salts which exhibit more ionic conductance. So by using third expression we can say that third expression is what? If number of ions increases, ionic conductance also increases. In this first case 2 ions are there, that is 1 Na plus 1 Cl minus. Here 1 Mg plus 2 and 2 Cl minus, that means 3. Here 1 Al plus 3 and 3 Cl minus, that means 4. So in this case number of ions are more, automatically this exhibits more ionic conductance. So the order is like this. These are competitive bits. So you should remember these expressions regarding competitive level. Next one, note. This is very important point. As dilution increases, dilution means addition of water. That means if water is added, automatically its concentration decreases. So dilution increases means concentration decreases. So if as dilution increases or concentration decreases, then molar conductance or equivalent conductance increases, but specific conductance decreases. First, why molar conductance and equivalent conductance increases when dilution increases? You see, the formula for molar conductance is lambda m equal to K into 1000 by m. The formula for equivalent conductance is K lambda equal to K into 1000 by n. In both cases, this is a concentration term. Here, this is concentration term. In both expressions, these concentration terms present in denominators. That means if concentration decreases, then this numerator value increases. That means the total value increases. That means lambda m increases. So here the point is what? As concentration decreases, that means m value and n value decreases, total value increases. So as concentration decreases or dilution increases, lambda m, lambda eq increases. So by using these expressions we can say that point. But specific conductance decreases. This is very important point. That is due to number of ions per unit volume decreases. I told you one more definition for specific conductance. That is, the specific conductance means the number of ions the conductance exhibited by number of ions in unit volume. The conductance exhibited by number of ions in unit volume, that is called specific conductance. That is the one more definition. So if you add more amount of water, automatically its volume increases. Amount of water volume increases. If volume increases, automatically number of ions per unit volume decreases. Number of ions per unit volume decreases. If number of ions per unit volume decreases, specific conductance decreases. So this is very important point. So as concentration decreases or dilution increases, equivalent conductance and molar conductance increases, but specific conductance decreases. So this is all introduction regarding electrochemistry chapter. We will discuss next topic in next video.